Hello, everyone. Thanks for joining this webinar. My name is Griffith Couser. I'm a policy officer at the European Polar Board, which is a membership organization which represents the polar programs of 29 different national research agencies, university, and funding agencies across Europe. So we are here at the Ocean Ice Introductory webinar, and Ocean Ice stands for Ocean Cryosphere Exchanges in Antarctica, Impacts on Climate and the Earth System. It's an EU-funded Horizon project and began in November of 2022. It's a member of the EU Polar Cluster. It is led by the Danish Meteorological Institute, and the British Antarctic Survey serves as the scientific coordinator. For more information about the project, I'm going to put the project website into the chat. It is ocean-ice.eu. And the sort of one sentence high level summary that I'm just going to read out is that it focuses on increasing our understanding of how the Antarctic ice sheet and the Southern Ocean, which surrounds it, influences our global climate, as well as reducing uncertainty surrounding the extent of the effects of ice sheet melt in the coming centuries. So the European Polar Board participates in Work Package 9 of the Ocean Ice Project, which is project coordination, dissemination, and outreach. As part of this, we conduct a webinar series, or we are conducting a webinar series on all of the Ocean Ice work packages. But today is an overall introduction to the project, so future webinars will focus on individual work packages, and they will all be available online. The web series is expected to continue throughout the lifetime of the project, so it will conclude somewhere just before the project itself concludes. The webinar is being recorded, and it will be available on the Ocean Ice YouTube channel. We will take questions at the end of the presentation, so you can ask them in the chat, or you can use the Q&A function. Everyone should be able to use the chat. And I'll start off by saying we have the Ocean Ice Project Coordinator, Dr. Ruth Mottram, introducing the project. She is a senior climate scientist with the Danish Meteorological Institute and got her PhD in glaciology from St. Andrews University. She focuses most of her work on the interface between climate modeling and ice sheet modeling. Unfortunately, however, she's not able to join us in person, or I should say live, because she's doing fieldwork in Greenland. So we have a video to play to introduce the project. And I'll also quickly introduce Dr. Andrew Meijers, who serves as the scientific coordinator for Ocean Ice. He's the deputy science leader for the Polar Oceans team at the British Antarctic Survey, and he got his PhD in physical oceanography from the University of Tasmania. He'll present following the remarks by Dr. Mottram, and he will also present the material from Sarah Coombs, who leads communication and dissemination of the project, but cannot join us because unfortunately she fell ill. But now I will play the video from Dr. Mottram. So give me a moment to share my screen here. And please tell me if there are any issues with sound.
So, good afternoon. My name is Ruth Mottram. I'm a senior scientist at the Danish Meteorological Institute, and I'm also the coordinator of Ocean Ice. And welcome to this webinar. We're very happy to see you all, virtually at least, and to tell you a bit more about this amazing project that we've got going. And thanks also to our host at the European Polar Board for inviting us and for setting this all up. We're really excited to talk about it. I am unfortunately not live online. I'm recording this just on my way to Greenland now, where we're doing some field work in the northwest Greenland, which is always pretty exciting too. I'm gonna share my screen, so I hope you can see my talk, and we will then get going. This in presentation mode. Good. So Ocean Ice is a Horizon Europe project, and it's a big collaboration. We have a number of 17 different partners representing 9 different countries within the EU plus the UK. And and about 8 million euros worth of funding. And this is both from the Horizon Europe, but also co-financing from the UK Research and Innovation to make this all possible. So it's a pretty big project, and we're going to be doing some pretty exciting science. I'm going to leave some of this to Andrew to really talk about the details. I really wanted to talk today about the motivation for ocean ice and why we're so interested in what's going on between the ocean and the cryosphere in Antarctica. I think that the first thing to say is, and this is not going to be a surprise to anybody, global sea level is rising. The global average sea level was record high in 2021, 2022. And what you can notice from this sort of image here that I've taken from NOAA is that sea level is not uniformly distributed around the world. So where the water comes from really matters. And this is why we really need to nail down what's contributing, how much, and how is that going to change in the future. If we look at the rate of sea level rise, it's actually accelerating. And so we tend to think, oh, sea level is going up about 3 millimeters a year, but actually over the last 5 years, it's been closer to 5 millimeters, 4.5 millimeters per year. So it's really an important thing to try and understand where the sea level rise is coming from, why is it accelerating, and how much is that going to accelerate in the future. And I think this was a statistic that gave me a little pause when I read it, that 10% of the last 30 years was actually in the 18-month period from January 2021 to August 2022. So we know that sea level rise does change through time. It can be quite variable on a year-to-year basis, but it's really going quite fast. And the cryosphere is now the largest single contributor to sea level rise. So initially, thermal expansion, the steric component, which is shown in blue on this graph here, was the biggest component. But if you look on any given year, the cryosphere is now starting to take over. The Greenland ice sheet is the biggest single contributor at the moment. I will just go back. The Greenland contribution is this pink line. And if you add up all the small glaciers in the world, they're actually giving the biggest contribution overall of all of the, if you add them all together. But Antarctica, which is just starting to show ice loss and contribution to sea level rise, has the biggest potential of all these ice sheets and glaciers in the world for sea level rise. If you look over a longer time scale, this is from the IPCC 6 assessment report, you can see these are the 2,000-year commitment and 10,000-year commitment. Now, 2,000 years is a very long time in the future, but I think it's probably worth pointing out that many European cities, Asian cities have parts of the city that can actually date back 2,000 years. It's not unimaginably distant. And so it's important to think about how we plan for this in the future. And what you can see here is that the Antarctic ice sheet contribution in meters, these y-axes are in meters, really starts to outpace the Greenland ice sheet contribution when we look on those kind of timescales. Having said that, the contribution from the ice sheets scales rather linearly with temperature, at least over these kind of timescales. What we have much less confidence in is what's happening on the short time scale. How abrupt does that contribution from the Antarctic and Greenland ice sheets start to come into the sea level, global sea level? So that was a very quick introduction to why we're interested in what's going on in Antarctica. Here we have a diagram which illustrates all of the different processes that are important in Antarctica. We have the sunlight, we've got shortwave, longwave radiation, we've got winds coming off the ice sheet plateau, we've got surface melt particularly on, this is a floating ice shelf here. There are some interactions with sea ice, we've got ocean coming in here. All of these things are really important to understand if we want to understand what's the surface, what's the ice sheet mass budget, how is that going to change, and how do all these different components interact with each other to affect how the ice sheet is changing. And so in ocean ice, we're going to try and really work with almost all of these. The objectives of the project are really to understand what's going on with the ocean in Antarctica. How is that interacting with the ice sheet, melting it from below? How is ice sheet melt going into the ocean and circulating into the global ocean? we really want to understand these sort of ice sheet ocean processes and put them into numerical models to try and understand the future evolution. Then we want to improve the representation of the ice sheet itself, the dynamics, and how was that going to change when we start to use coupled climate and ice sheet models, which are still pretty, there are very few of them around, and many processes that are actually important and not very well represented in these models. So that's really an area of focus here. And then we really want to understand how does the sensitivity of the melt, what is it, the sensitivity of the melt over the ice shelves? You can see that we already have surface melt here. There are many ice shelves in Antarctica that have quite a lot of surface melt already, but how is that going to change with climate forcing? And this is in particular important because the surface melt may well lead to more unstable ice shelves. We're very interested in the freshwater flux from Antarctica, not just in terms of the sea level rise component, but also how does that affect ocean currents. Then we also want to look at the global ocean, as I mentioned, and how that's going to reflect back on other climate indicators around the world. And then we're committed very much to free, open data, contributing to international assessments, developing climate models, and then interacting very much with policymakers, which is something that I do in my day-to-day life very much at the moment. For us in Denmark, it's a low-lying country, and the loss of the Antarctic ice sheet is really potentially an existential problem. It's not easy to understand how we can adapt to the kind of sea level rise that we could potentially see if we see a large-scale loss of the Antarctic ice sheet. I want to leave you with this image. This is the Crane Glacier, which is a fairly notorious glacier in Antarctica. And this is after the Larsen B ice shelf collapse. This glacier saw a large increase in speed, but it actually really carved back very quickly, which you can see here. So this is April 2002, 2003, and then by 2006 it was here. And this behavior was a little bit unexpected. So it was actually a bit of a wake-up call to the glaciological community that we really need to understand these processes. And I think I like this picture because it really sort of implies that we need to understand both gradual change but also abrupt change to really understand if there are tipping points out there. So with that, I'm going to stop here. That was a very quick overview of what we're interested in and what we're trying to look at with ocean ice. And I will hand over to the rest of the group. I hope you enjoy the rest of this meeting.
So that was the project coordinator, Dr. Ruth Mottram, and now I will throw to Andrew Meijers for his bit.
Right, so thank you very much, Griffith, and thank you, Ruth, for that very helpful introduction. So yes, I'm the scientific coordinator for ocean ice. And as Ruth said, this is a large Horizon Europe program that's co-funded by the EU, but also by UCRI, the UK research. And it's coordinated by DMI, and the scientific leads are Bass and myself. And then there's 17 centres across Europe and the UK, all working towards the goals that Ruth enunciated just now. So while Ruth is a glaciologist, I'm a physical oceanographer by background, and so I'll just give a couple more bits of motivation for ocean ice in general. So as Ruth alluded to, sea level rise is probably one of the biggest climate uncertainties over the coming century. And one of the reasons for that is our relatively poor understanding of the processes that drive ice-ocean interaction and our even poorer modelling of those interactions and feedbacks. So on the right here, you can see this plot coming from the IPCC Assessment Report 6 of a couple of years ago. And this is showing the global mean sea level change for the coming century under a variety of different climate forcing scenarios. And you can see that the very top range of a strong business as usual type scenario is pushing 1 metre. But that does hide the fact that the coupled climate models that are used to make these projections basically treat Antarctica as a cold rock. Antarctica can't melt in these models. So anything that basically all it can do is let the snow that falls onto it run off as meltwater. It can't actively interact with the ocean, it can't melt back, and it can't lose its ice sheets. And that's really due to our limited ability to model this in these, and particularly to couple the ice sheet to the rest of the climate system. So the IPCC addressed this deficiency basically by doing an expert survey, which is maybe less than scientific. It was done rigorously and carefully, and it did produce this dashed line here, which is the low likelihood but high impact storyline, where there's ice sheet instability processes allowed and significant meltback of the Antarctic ice sheet. And you can see there that pushes, it almost doubles effectively the effective sea level rise under a strong forcing scenario. But it's, like we said, it's not modelled, and it's structured expert judgment, which is, some might say, a bit of guesswork, which I'm doing it a disservice. But you can see it's really not done to the same level of rigour as the rest of the climate system. Yet we can see from our observations over here on our left, this is from ISAT mass losses for both Greenland and the Antarctic ice sheet, that there is rapid meltback of Greenland. So as Ruth said, Greenland is currently the greatest contributor to sea level rise. But Antarctica is accelerating, and particularly in the West Antarctic and parts of the East, there has been very significant meltback in recent years and accelerating. So this represents a huge uncertainty with massive potential global impacts that is presently not well modelled for a variety of reasons. So here they effectively state this in the IPCC: there is deep uncertainty, and so there's low confidence in ocean forcing affecting basal melt rates. We know it happens, but we have low confidence in projecting it and in simulating the mechanisms that can cause rapid ice loss through marine ice cliff instability. So the main issues here is there's no coupling between the ice sheet and climate. They don't effectively talk to one another in climate models. There's a lot of initial state biases. So, for example, precipitation over Antarctica, and particularly the ocean sea surface temperature, is often too high. So if you do couple your ice sheet, suddenly it responds in an unphysical way because the boundary conditions are not accurate. And there's a real lack of process understanding in how the ocean delivers heat to the ice sheet, how that is actually affected as basal melting underneath floating ice shelves. Surface-driven melt, so the formation of melt ponds that Ruth was talking about, and how this runs off both on top of and below the glaciers. And particularly things like marine ice cliff instability and iceberg formation and subsequent ice sheet dynamics and collapse are also really not integrated into coupled climate models, and even in custom models specifically designed for glaciological conditions are still somewhat poorly understood. So ocean ice is really trying to address that, and here's an example of the sort of impacts that we're talking about. On the left here is basically showing the change in the global surface temperature relative to when you add a realistic or estimated amount of fresh water from the Antarctic melting to a coupled climate model. Down here you can see the red line, which is the control simulation with no fresh water, and the blue line is the simulation where you've just added fresh water. You haven't done anything dynamical. There's no feedbacks between the ice sheet. You've just added the fresh water that you would expect from a standard melt scenario. And what you can see is the globe is actually significantly cooler. Basically, you've added a lot of cold water and you've increasingly stratified the top layers of the ocean. And so the actual atmospheric temperature, the sort of 1.5 degrees that we talk about with the Paris Accord, it's actually slightly cooler when you add that ice in. But what you see beneath the ocean, and so this is the temperature difference between that control simulation and the freshwater simulation at 400 meters under the ocean surface, you see actually there's a very significant warming around Antarctica of up to 2.5 degrees, which for those areas is massive. And what that is actually effectively saying is that by adding that fresh water in, you're trapping heat beneath the mix layer and allowing it greater access around Antarctica, where you would expect in a coupled model, you would actually accelerate that fresh water. So this is something of a positive feedback with more stratification at the surface and accelerated heat and melt at the depths where ice sheets intrude into the ocean. And that leads to the next question of what about tipping points? What about sudden dramatic changes that Ruth mentioned? And you can see here that the Antarctic and the cryosphere system includes many of the identified tipping points. So this is from a study that came out last year, Meteorological, and you can see actually 1, 2, 3, 4, 5, 6 of the tipping points that have been identified there are really associated with very high latitude changes. in ice sheet ocean interaction. And those tipping points here are represented as individual discrete events, but there's no reason to believe that one tipping point wouldn't interact with the rest of the climate system. In fact, you would expect it. And so conceptual tipping point cascades have been talked about in statistical senses, and certainly not modelled in like a climate model, but there's been lots of analysis, or at least an increasing amount of analysis done, looking at how you would expect things like the disintegration of the West Antarctic ice sheet to feed back onto things like the Greenland ice sheet, changes in the Atlantic and meridional overturning circulation, and then feed back into more terrestrial sorts of critical parts of the climate system, such as the Amazon rainforest. So what we're hoping to do here is start looking in ocean ice, start looking at this in a more rigorous model-based fashion. And to do that, we've drawn together expertise from a number of really relevant projects. So each of these aspects has been looked at in some detail recently by European or UK research groups in large coordinated projects. And most of these are ongoing. So Protect has been looking at the changes in land-based cryospheres, so the ice sheets and glaciers, and seeing how that directly drives the sea level. TIPAX has been looking at the likelihood of large near-future changes in sea level rise. So that's basically looking at tipping points. And SOCHIC and Orchestra, so this is an EU and UK respectively projects, have been looking at how the Southern Ocean really is critical for taking up heat and carbon, but also delivering heat to the Antarctic ice sheet. And all four of these projects are represented within Ocean Ice. And in fact, the coordinators for every single one of those are members of the steering committee or key scientific members. So we're really amalgamating this expertise in these different components of the Antarctic climate system and bringing them together to address these questions. And there's also been a recent improvement in the tools that we're using. So as I mentioned before, none of the CMIP6 sets of models, a couple of climate models used to inform the AR6, included active ice sheets, but that is something, an area of active development. And so the UK ESM model, so that was one of the climate models that did contribute, has recently had a successful coupling of the climate model to an Antarctic ice sheet. So that was published earlier this year, in fact. Allowing for this dynamic feedback between the ice sheet and the ocean and indeed the atmosphere and the rest of the climate. And you can see some quite dramatic results there. This plot here basically shows the integrated melt flux from the Filchner ice shelf in the Weddell Sea from a control scenario, which is the black line, where there's no coupling, and the red line where there is a coupling. And basically by 2100, pretty much nothing happens to the melt rate because the Weddell Sea is actually very, very well insulated from changes in the ocean circulation. But by 2100, the forcing has basically burnt through this protection, and suddenly you see a really rapid increase in the rate of melt, which is suggestive of these potential positive feedback effects. So Ocean Ice will take this model, this expertise and other tools and start to integrate them together to address these questions. So Ruth touched on these objectives, so I will skip over that in favour of more graphical representation. So what we're hoping to do, this is effectively a graphical layout of the project setup. We're hoping to look at the interaction of the subpolar ocean and heat delivery to the Antarctic ice shelves, and understand both how that happens and the subsequent ice sheet dynamics. Using those boundary conditions to inform improved ice sheet historical reconstructions, and improved dynamics within the models used to reconstruct the Antarctic ice sheet's history over the last 30 or so years. And then starting to project how we expect the ice sheets to change under a variety of forcings, and really try to rigorously constrain the uncertainty involved there, so we can really start getting a handle on how much freshwater we expect to come off from the ice sheet, in what form, and with what level of uncertainty. Those freshwater fluxes under different climate forcing scenarios will then be used to force ocean models, so ocean-only models, not coupled ones, to look at how the very long-term changes in the ocean circulation react to these extra freshwater, but also freshwater that has been estimated in a realistic sense. So we can put bounds on how we expect the ocean circulation to change, And it's worth noting that while this is mainly Antarctic focused, ocean ice does include a small Greenland component. So we will have freshwater fluxes from Greenland there to force this question as well, and also address the question around northern versus southern drivers of the Atlantic meridional overturn in circulation. And then we'll start using the coupled models, which we talked about before, to start looking at how those these sorts of changes in the Antarctic ice sheet produce feedbacks between the ocean and the ice sheet, whether those are negative or positive or some combination of those in different regions and different mechanisms, and then start looking at how that impacts large-scale global metrics of interest, mainly mean sea surface temperature and sea level rise, but with potential for applications to things like the Greenland, Amazon forest dieback or changes in permafrost melt, where those are available in the models. And finally, it's very important that we communicate these things. There's no point just doing it and keeping it to ourselves. So we'll be taking active roles in climate assessments, things like contributing to the IPCC reports, CMIP 7, and providing direct advice to policymakers and the public. So the program is arranged effectively around those ideas, where the first 3 work packages are really looking at processes. So these are looking at the subpolar processes around Antarctica, looking at the ocean heat delivery to and from the ice shelves, looking at the ice-ocean interaction directly, particularly underneath floating ice shelves, and the ice sheet dynamics of the Antarctic ice sheet itself. So modelling more accurately the ice sheet. And then moving into more impact-focused work packages. So this is delivering those later objectives, looking at how the ice sheet will change in the future and the freshwater fluxes coming from that, how those freshwater fluxes will impact on the ocean circulation, and then ultimately looking at beyond just the ocean circulation, but to the global climate and how a coupled ice sheet climate model differs from purely climate models without an ice sheet. And of course, there's a number of supporting work packages there. Data management is we have a number of observational programs as well as models. And so data management and making that free and openly available is being handled in work package 7. This is also tied in with SOOS, which is the Southern Ocean Observing System, who are direct partners here, who will be providing an update and layers to their SOOS map technology to make this more available to the community in an accessible format. Work package 8 is scientific coordination. This is actually led by myself, which will be making sure that the work packages are both coordinated internally, avoiding sort of siloing, and identifying a number of really cross-cutting themes there. So they're shown by these icons, basically looking at where each of these work packages, which have their own focus and deliverables, really should also be looking to the other work packages to look for synergies and collaboration opportunities. And finally, work package 9, which is dissemination and outreach, which is looking at making sure that we're not doing this in isolation and we're reaching our stakeholders, policymakers, and the public. And all of this is overseen by a General Assembly, Scientific Steering Committee, and an expert advisory group, which is independent. So obviously, this is not manageable by any one person. So we've had to bring together expertise in all areas of the ocean, the ice sheets, and the wider global ocean circulation. And so here are the people that you should go and talk to for your favourite piece of this puzzle. So in work package 1, so this is the oceans area. That's Pierre Dutroux and Marcus Janart at ARVI. Nicola Jordan and Anna Varlan at IGE and Newt Gothenburg are looking at the ice sheet's ocean interactions. So Ruth, who's the project coordinator at DMI, and Gail Duran at IGE are looking at the present-day Antarctic ice sheet modelling and representation. For looking into the future and really constraining those future projections, that's Jan de Roos and Frank Patton. Then we have a Norse team, which was purely accidental. But that's work package 5, looking at the wider ocean response. So this is largely focusing on the AMOC, but not entirely. So that's Elaine McDonough and Petra Langeroux. And work package 6, which is really the integrating work package where we look at the wider climate response. That's Ricardo Winkelmann at Potsdam and Tony Payne at Bristol. And so data management is being handled by ETT, and that's Antonio Novellino. And finally, work package 9, the dissemination and impacts, Sarah Coombs here at BAS, who unfortunately couldn't be speaking today, and Renuka Bate at the European Polar Board. So these are the people to reach out to for expertise in your area. So now I'll take us through basically what we intend to do in a little bit more detail. So it's sort of in two phases. There's sort of a more Antarctic focused, process focused set of work, and then a wider global synthesis. So, and I guess it's also worth noting that we have a very wide variety of project partners. There's the EU Polar Net. Ocean Ice is part of the EU Polar Cluster. We're strongly linked in with Copernicus and via the ETTs, making sure that our data is available. SUS, as I've alluded to, are project partners. And we have strong connections with ESA and SCAR as well as being in key areas of interest. So just walking us through this complicated diagram, hopefully just paying attention to the bright bits. So we'll be looking at the Antarctic ice sheet mass balance and its freshwater flux modelling. So this is really trying to model the present day ice sheet. And so that'll be making advances in getting the surface runoff more accurate, allowing for blowing snow and basal melt of the grounded ice sheet, and using that then to provide a hindcast of the recent past and present day freshwater fluxes. So really trying to match the models to what we have observed in the altimetric period. For work package 2, we'll be looking at doing some AUV deployments beneath the West Antarctic Peninsula. So these are the infamous rapidly melting ones, which are relatively warm. So the circumpolar deep water has access to these. And particularly looking around grounded icebergs, looking at the dynamics of heat delivery, basal melt mechanisms, and how the ocean, iceberg, sea ice, and bathymetry interact. So we'll be using an AUV deployed there. And I guess also looking at these flags here, these are nations that are supporting our efforts. They're not part of the project directly. They're usually non-EU nations, but they're project partners who are providing logistics and scientific expertise to really make this happen. So for example, this AUV will be deployed by the South Koreans off Pine Island, Thwaites area. We'll be doing some active model development, mainly to the NEMO, to allow iceberg interaction with bathymetry and sea ice. So you can see this model development ties in quite closely to the observational efforts of grounded icebergs. Grounded icebergs are important in the sense that when a large iceberg grounds, it opens up or closes, as the case may be, large areas of, modifies the sea ice and potentially allows for plenty of formation or destruction if the iceberg moves away. Which is very important for dense shelf water formation and regional circulation, and in fact global circulation. That's presently not modelled in NEMO, and so we'll be adding this ability to the NEMO cluster, to the NEMO nucleus, and as well as that, we'll be adding including the ability to model oxygen isotope traces, and oxygen isotopes are an important mechanism for tracing freshwater sources. So we're improving our ability to model that. So in contrast to the under warm ice shelf, we'll be looking as well under cold ice shelves. With support of the Norwegian program, we'll be deploying instrumentation through boreholes drilled by BAS underneath the Fimbul ice shelf, which is a cold ice shelf, and looking at the mechanisms and basal melt in that region. And novelly including oxygen isotope measurements, basically in near real time, measuring oxygen isotopes coming from basal melt. We'll be also undertaking a relatively large program of circumpolar mooring and instrument deployments, and adding to existing mooring arrays in regions of key ice-ocean interaction. So we're quite interested in looking at how, as well as getting heat on and off and freshwater off the shelf, how circumpolar transport around the Antarctic continent both moves recently formed meltwater, but also delivers heat to regions of melt. So one particularly infamous area is here, where in the Munson-Bellinghausen Sea, increased melt from the ice sheet is modifying the water that moves around the coastal current and ultimately ends up in the Ross Sea, which then has been associated with reduction in salinity, a reduction in density, and a consequent reduction in Antarctic bottom water formation. So again, you can see there's many nations helping us with these observations, and much of this will be achieved through the deployment of an array of Moderator. And so that's slightly facetious, but these Argo floats will be deployed over the shelf and then told to dive deeper than the shelf is, effectively making them ground on the bottom. And so when they profile, they'll take a profile and then sink back down and get stuck again, hopefully. Meaning they won't actually move very far, and they'll act like quasi-moorings. And the idea is to keep them there throughout the wintertime. So there's obviously many we have very poor understanding of the Antarctic oceanography in wintertime, particularly underneath sea ice. And so we're hoping that these, deployed in a circumpolar fashion, will give us some new insights into that regional oceanography and the transport from region to region. We'll also be making extensive use of Earth observation satellite data and use that to develop some new products. So one of these will be sea ice production and using that to monitor shelf circulation where we can, using some of the new products that look at dynamic circulation in the presence of sea ice. Work package 3 will be looking at on the continent to start deriving melt lake depths over the ice sheet and to start building bespoke consolidated data sets of surface ice damage and calving front locations. This is really important for understanding the dynamic question of how the ice sheet responds to forcing. So now zooming out a bit to look at the Antarctic in its global context. We'll be undertaking a number of global research elements. So the first will be exploration of the deep uncertainty. So this is really looking at that question of how the ice sheet will melt into the future. So we'll be running model simulations, both coupled and uncoupled, over the coming century, but also to 2300. The Antarctic ice sheet is a very long-term process, and we believe that starting to plan on multi-centennial timescales is not unreasonable to start delivering to policymakers, because it's a problem that won't be going away. And so these simulations will really work to explore the parameter space of the ice sheet dynamics, and including tipping points, and trying to really robustly quantify the uncertainty associated with these. That will be used then to feed freshwater fluxes. So looking at the spatial distribution of this freshwater discharge. So presently, models often fairly naively dump all the freshwater in evenly around the Antarctic ice sheet, and usually at the surface, which is not at all how it's done in reality. So modelling will be done to improve this based on the subglacial hydrological models. And then also modelling the ocean response to a range of these different freshwater scenarios. Some new observations will be made in a presently known but completely unobserved Antarctic bottom water pathway from the Weddell Sea. So this is in the South Sandwich Trench. So BAS maintains an array of moorings in other exit pathways from the Weddell Sea, but this is a huge gap in our knowledge and something that's been identified by the SOSHEET project. So we'll be adding instruments in the South Sandwich Trench to really close off the Weddell Sea observationally and really monitor this important and reducing pathway of reducing water mass into the future. This water mass does move up the Atlantic and is observable at the Samba Array, which is an array of moorings that go between Brazil and Africa, and is maintained by Brazil, Argentina, and South Africa. So we're part of we've worked in collaboration with the SAMOC Consortium, which is looking at the South Atlantic overturning circulation, and is part of the Atlantos and All Atlantic Ocean Research Alliance. So we'll be looking at how we'll be instrumenting these arrays with extra instruments to look at the bottom water properties, which are presently unmeasured, and starting to use that to link up our longer term understanding of where this bottom water is going and changing with what's happening immediately around the continent. So then we'll be using our model-based assessments of the impact of this melt in the Antarctic and Greenland on the Antarctic circumpolar current, the upper ocean circulation, and the AMOC. So we'll be looking at a range of scenarios. This is when you're talking about the importance of the two poles in driving the AMOC. You're really talking about millennial timescales, because that's basically how long it takes water to circulate. And to really look at the relative role of these two poles and melt in those two poles in driving the AMOC, and doing that both in coupled and uncoupled configurations, although the coupled configurations will have to run for shorter timescales. And then finally, looking at the global impacts of these ice sheet melting feedback. So this will be using the PISM-MOM ensemble to look at multimillennial timescales. So this is really ice sheet ocean only, so no atmosphere, under different atmospheric forcings. and really to look at how much, look at the potential for locked-in change and the potential for tipping points and cascading tipping points on long timescales. While the UK ESM will be run on sort of centennial or 2300 timescales using fully coupled ice sheet ocean climate and looking at a range of coupled SSP scenarios, as well as some of the high-end work package 4 scenarios where we're looking at that possible tipping point type melt. And using that to assess how that changes the global metrics of interest, so sea global mean surface temperature, sea level rise, ocean heat content, and some of these extra polar tipping points. And finally, there's outreach, which I'll cover later in Sarah's talk. So here's the experimental design. I guess it's sort of obvious from what I've been saying, but we'll be producing these Antarctic ice sheet freshwater fluxes out to 2300 under these different forcing scenarios with associated uncertainty bounds. Using that to partition the fluxes into its main components, which is the ice sheet basal melt, surface runoff, and iceberg carving, and understanding the probability distributions of these fluxes for upper and lower bounds. And then using these scenarios to define a number of hosing experiments where we basically flush this water into the ocean, hopefully in a more rigorous way than just dumping it at the surface everywhere. Into forced ocean models and assessing those on centennial and multi-millennial timescales, and also acknowledging the fact that the Greenland ice sheet is important too, and using modelling there to impose similar freshwater flux runoffs. And then basically looking at how this changes the ocean circulation, focusing on the major cells, so the upper and lower overturning cells, and how that delivers heat to the rest of the climate, or how that basically changes the ocean's interaction with the rest of the climate. So you can see that it's a very highly interconnected project. So this spaghetti diagram basically shows all the different tasks and how they relate to each other across the work packages. I won't bother going into them, but I guess the intent here is to show that we've put quite a lot of thought into the different elements of this and how they should communicate with one another. And these are basically associated with deliverables, which the EU will hold our feet to the fire to make sure we do. And then we've identified these other cross-cutting themes, which are sort of more scientifically nebulous, but potentially very interesting, where we'll be drawing together the people across the work packages in the program to talk about these, but also increasingly incorporate expertise from outside the program to really focus on the potential to advance our understanding of these different themes, namely freshwater fluxes, the export of Antarctic bottom water, the wider climate impacts of the Antarctic ocean coupled system, and exploiting these isotopes, oxygen isotopes. So there's a number of themes, a number of elements looking into the utility for oxygen isotopes and understanding freshwater fluxes across the project, both modelled and observed. So that's basically it. This is our ambition. We really want to be making the first global climate projections, maybe the IPCC class Earth system model, and including potentially the collapse of the Antarctic ice sheet, or at least regions of it, producing new estimates of Antarctic ice sheets freshwater fluxes under a range of scenarios with associated uncertainty bounds, to improve our quantification, improve our quantification into the future, and to understand the importance of iceberg distribution modelling and grounding around Antarctica, and how that impacts the above freshwater fluxes and indeed climate impacts. Looking at observation-based quantification of radial exchanges, making new observations of iceberg interaction with bathymetry in the sea ice with AUVs, unique observations within contrasting warm and cold ice shelf cavities, extending our prediction of ice sheet surface runoff, which is really something that has been not ignored, but maybe not given the attention it deserves, and making the first observations of this South Elmage Trench Antarctic bottom water pathway and understanding how that feeds into the wider South Atlantic variability. So that's it, I guess, on the science side. This is the talk that Sarah would have been giving if she were not unwell, and she extends her apologies. But I'll talk briefly about our communication and dissemination plan and how you can interact with us. On the left, this is Sarah. She's supporting the project coordinator and the UK coordinator. it keeps an it keeps an oversight of the project deliverables and milestones. And Ruth H Mottram is basically essential in keeping everything working. She's directly supporting the coordinators and helps with the social media and website updates. And so on the communications and collaboration side, we're going to be delivering a communication strategy, targeting the stakeholders, developing a strong visual identity so people will know that we're Ocean Ice. And there'll be lots of project outputs around social media events and creating outreach materials, not only for specific events, but also more general levels, and aimed at a variety of end stakeholders from schools up to policymakers. In more concrete terms, we'll be running 2 policy briefings. This will be organised through the EPB. One will be early in the project to raise the profile of Ocean Ice and its ambitions with relevant policymakers, particularly in the EU. And then another late in the program, along with a white paper on what we've achieved and what we've found, provided in a policy relevant context. There'll be lots of, obviously, scientific conferences and workshops, webinars such as this. We'll be promoting results. And those scientific conferences and workshops will really be sort of hung off existing conferences and aim to value add to those, raising the profile of Ocean Ice and bringing together experts to discuss the topics that Ocean Ice is really interested in. And we'll be communicating to a full range of stakeholders. And I think it's important to underscore the involvement of Ocean Ice in assessments. So things like development of the upcoming CMEP 7, things contributing to inter-comparison projects such as TIPMIP and looking at ice sheet melt MIPs. So we have many of the members of Ocean Ice or the advisory board are actually directly leading members of those consortia. So we'll be taking a key role there. This is a nice impact matrix that I think we stole more or less directly from Protect. So thanks, Protect. Nicely sort of laying out our plans. So this is effectively who we're trying to reach, from researchers right down to the general public, and the sort of level of what we're aiming for, basically from awareness, which is sort of the stage we're at the moment, raising awareness of what we're doing, to dissemination of our results, and then finally to exploitation and actually making an impact with those results, which will obviously be happening later on in the project. But you can see the range of approaches being taken here, from websites and social media, which is where you'll be seeing most of what we're doing at the moment, seeing as the science is still in a very early stage, associating with other projects through areas like the Polar Cluster, and popular science events, just making outreach and general awareness raising. And these will move on as the project progresses into obviously scientific publications, new data repositories. We'll be undertaking training and workshops, particularly for early career researchers, and then moving up to concrete targeted things like policy briefs, model inter-comparison projects, and ultimately things like climate assessments. So here's where you can find us. There's a wide range of social media. Our website is up and being developed, and you can reach us through any of these means. All are actively monitored, as well as the good old-fashioned just send me an email. And as for what we've done, we've had a kickoff meeting. We've joined the EU Polar Cluster, taken part in ESA co-location meetings. So these have really been actively in raising awareness for these groups that Ocean Ice is here, what we're going to do, and how to coordinate with us. And some of those are either directly scientific, such as the Polar Cluster. Others are more sort of policy focused, such as in getting involved in the All Atlantic sister project in communications, which has a very strong policy focus. And also public outreach. So Ocean Ice, so Antonio Novellino at ETT has been selling our story at the Ocean Race, which is basically a yacht race. So it's a good way of reaching a Southern Ocean and ocean interested public. And finally, for future events, and probably most importantly, how you can engage with us. So there'll be an Ocean Ice themed breakout discussion at the upcoming IUGG meeting in Berlin. That will be announced, its dates in April, along with the IUGG program. But the intention there is to provide a forum for 2 in particular sessions, which are cross-cutting ocean cryosphere themed settings, symposia to actually provide a moderated discussion forum to allow sort of more detailed discussion of the talks and the general themes that are emerging out of those sessions. The Sue Symposium in Hobart in August this year, Ocean Ice is running a session. I'll be running a session. And that's really focused on circumpolar Antarctic observations, and particularly how these observations can be most optimally used to support model development. And there's a workshop with ESA CCI, really focused on Earth observation and ice shelf mass balances and improving communications between the Earth observing community, the cryosphere community, and the ocean community. So that's being headed up by Ruth Mottram and will be in Copenhagen on the 23rd and 24th of May. So invitations for that are now open, so please get in touch if you're interested in attending. And then there's a variety of, these are the most concrete events that are specifically Ocean Ice, but I'll probably leave this for you to read, but there'll be many other events where Ocean Ice will be having specific either public outreach efforts or taking an active scientific role. Maybe I will highlight some efforts that we're making to integrate Ocean Ice with our early career researchers and early career researchers from elsewhere. There will be a summer school. This is preliminary, but hopefully organised in collaboration with SOCIC, mainly led by Jean-Baptiste Sely, which will be in summer 24 next year in Corsica. So looking at, this will be largely ocean and Southern Ocean processes. We're hoping to run boot camps for early career researchers to really accelerate both their scientific work, but also their integration and collaboration with one another, and then getting involved in more sort of casual events such as climate coffees. So please, if any of these interest you, please reach out through the variety of emails that are here. And so I think with that, I've used up all of my time, and I'll be happy to take any questions that you have.
Thank you so much. That was a very comprehensive, broad overview of the project, so thank you for that. We don't have any questions from the audience just yet, but I'm going to use this opportunity to tell everyone to please go ahead and ask any questions you have in the chat or with the Q&A function. And in the meantime, while people are considering that, let me go ahead and ask you a couple of questions that I have. And in typical fashion for me, I'm going to start off with something a little bit, I don't know, provocative or negative. What challenges do you see in the future for the project work? What are the risks that maybe we don't achieve all of the objectives that we've set forth? Do you see any hurdles coming up?
Yeah, I mean, I think it's very ambitious, particularly in its modeling ambitions. So I think the most challenging thing will be, I mean, I think probably the most valuable data set that will come out of this will be the very rigorous uncertainty estimates around freshwater fluxes. So coming out of work package 4, because those things are very actionable. Those and their uncertainty bounds are the sort of things that you'll be able to stick on pretty much that plot that we saw earlier from the IPCC, and say with confidence, this isn't a survey, this is backed up by some very rigorous dynamical analysis, but also statistical approaches to understanding quantifying known unknowns, unknown unknowns, and those sorts of things. So I think that's very, very achievable, and I think that is what we will be delivering and really waving our flag around. The harder things, I think, will be trying to do some of these global impacts, because as I mentioned, this really relies on getting those coupled climate models right, and those coupled climate models, particularly coupled with an ice sheet, is very new science. So I think we'll be really pushing forward the boundaries of our understanding of those, but understanding and certainly providing the same level of rigor as we might hope with the freshwater fluxes to things like tipping points. Those are going to be less well constrained, but like just by default of the fact that we don't have as many models, there's lots of process understanding that needs to go into that. So we're really going to work on refining that parameter space and understanding a lot of the uncertainties and the unknown unknowns that we haven't got there yet. But yeah, I think that will be the most challenging bit, and that will be the bit that comes with some caveats, I'm sure, or scientific caveats anyway.
All right, thanks. Yeah, you touched a bit on one of the modeling questions that I was hoping to ask, but let's go to Clara Wilcock. do you have any idea on when the boot camps or other researcher courses will be offered?
Okay, yeah, so it's an idea that's coming. So based on the success of a recent Polaris boot camp that was held, I think in Norway off the top of my head, that Ruth was also a part of, they were looking at using CMET models to assess changes in the Arctic. So that was a really successful 3 or 4 day workshop, and we were hoping to emulate that. So it won't be happening this coming year, mostly because, I mean, the main reason pragmatically for us is a lot of our early career researchers are still yet to be recruited, but I think a lot of those will be in post by next summer. So I'm hoping that in May, probably late 24, we'll be hoping to have some boot camps. And I think, I mean, there's an obvious call for a Southern Ocean CMET style boot camp, but also just in the sense of bringing together researchers within the same field and sticking them in a box for a few days where they can both talk about their research and their findings and really work at pushing that forward with some more senior researchers there to really provide guidance and expertise. So we don't want to hold it at the same time as the planned Corsica meeting, so there will be some juggling around of dates to make sure that we're not putting everything on at once. But I would expect summer 24 and probably another in 25 for those.
Yeah, I was going to say there's the Corsica thing is the only thing I know is planned, but that's technically through SOCHIC.
That's right, yes.
Yeah.
Meijers is making a contribution to that and we're providing researchers, but SOCHIC is the lead on that.
Yes. Good. Well, again, if anyone has any questions, go ahead and ask them in the chat. But otherwise, I'm a policy officer, so I'm going to ask you a kind of policy question. So Antarctica is pretty far away from Europe, geographically speaking. So what do you think are some of the most effective methods of communicating some of the outcomes of the models that you're going to generate to European policymakers who may be more focused on the immediate impacts at home rather than the centennial timescales that some of these things are operating at?
Yeah, I think there is definitely a challenge. I think it's not so much the remoteness that people suffer from. I think people are pretty across the idea that if you pour water in at one end of the world, it very quickly moves across the other side of the world. So sea level rise is a global issue no matter where it stems from, with some caveats around gravity and things. So that's not so much of a challenge. And I think sea level rise is very much on the mind of many European nations, particularly the low-lying countries. And the UK, I know, is also looking into producing an expert panel on understanding sea level rise. The centennial part is a challenge. So I think one of the strengths of this project, and I didn't really mention it here, but we have a partner project, EPOC, which is being led out of Hamburg, who are looking at a sort of more North Atlantic centric aspect of this question, but they'll also be addressing some of the questions around sea level rise and circulation changes. But their focus is more on the decadal to multi-decadal timescale. So there's a very strong synergy between the two projects where they can provide some of that more instantaneous feedback to policymakers, while we can provide the long-term consequences of current day inaction. So I think what we need to make very clear is that the choices we make now affect what happens in those 100 years. And so while that's not an electoral timescale, I think people do think on those timescales, particularly people like coastal engineers and the people who do that sort of planning. That is an important timescale. And the inaction now, I think it also really strengthens the motives for actually making changes now rather than just preparing for a sea level rise, but actually hoping to avoid it to the extent we can.
Thank you. Yeah, it's a bit of a loaded question there, but I'm gonna keep on that theme. Maybe I'm abusing my moderatorship here a little bit, but here we are talking about decadal and centennial timescales, but a lot of the climate impacts that we're talking about are essentially generated by human activity, right? So how can we accurately predict into that far into the future the human impacts on a lot of what's going on?
Yeah, so I think for that we'll have to lean a bit on the experts there. So there's the various SSP scenarios for future climate forcing. So the IPCC has put together basically a matrix of potential human impacts. and the mechanistic responses, so the effective CO2 forcing that those provide. And those provide a variety of industrial, economic and social factors. So you can basically pick and choose if you think there's strong social change, but maybe not so much economic change or rapid change. So you can basically pick the sort of scenarios that that are maybe useful for bounding understanding. So you could look at a very strong mitigation scenario where everyone gets their shit together and actually does something rapidly, versus a business as usual or even an accelerated forcing scenario that sort of produces an upper and lower bound. And so, I mean, these have been thought through fairly rigorously by people who understand those aspects. It's certainly not us. But the other thing is they're standardized. So you can sensibly compare your output of your model output with model output from others that have been forced by these sort of standardized scenarios. So I think that's what we're using to guide things.
All right, fair enough. We have another question in the chat here, and I apologize in advance for the way I'm going to pronounce your name, but it's Shenji Zhu, who says, thank you, Andrew. And something really interesting that you mentioned in the talk is that the ocean-only simulation will be using the freshwater fluxes with variable vertical distribution as the boundary condition. What do scientists involved in the project expect on this particular aspect? Any large-scale freshwater flux data will be produced. If so, will this be derived from the observational data produced within this project or any other source of data beyond the project, including modeling and climatological data products?
Yeah.
So thank you for that question.
Yeah, thanks, Shenji. So yeah, like I said, yeah, the freshwater fluxes are a really key output because they're actionable. You can turn them into sea level rises relatively easily. So yes, we are producing those large scale freshwater fluxes. They won't, but they will be coming from models. But those models in turn will be informed by our understanding of the observed ice sheet change. So I guess the observations are really working on the process level understanding of how the heat actually melts, or how the various different melting processes occur and what they respond to in terms of forcing. Integrating those into models is not trivial, but there are a variety of ways that you can tweak your models to particularly in parameterizations, to more accurately represent the processes that we see. So that is sort of work package 2, which is representing those processes, and work package 3, which is improving our modeling of that. And then work package 4 will take the findings from those on board. Obviously, it's quite tricky to do all this because it takes years to make process improvement, but at the same time, you need to be producing your fluxes early so people can use those. So it'll be a bit of an iterative back and forth process, but ultimately those improved observational constraints and model improvements will feed into the freshwater fluxes. That will be one of the major outputs, both on its own terms and also as boundary conditions for the ocean circulation experiments. So I hope that answers it, Shenji. Yeah.
Good. Yeah, thank you once again. We're coming right up to the end of our planned time. I think I scheduled this slightly longer just in case of time overruns, but it was meant originally to be about 60 minutes. If anyone has any other questions, I would encourage them to put them through the chat right now. Otherwise, I think we're good to wrap up. So thank you very much for the presentations. I just want to reiterate, this is the very beginning of a multi-year project. So there will be outputs and materials coming out along the way. So please follow us and keep your eyes out for those. So again, thank you to Ruth Mottram for her presentation, and of course to Andrew Meijers for his presentation, and to the audience for the questions and for your attendance, as well as to the EPB Secretariat for supporting setting up this webinar and communicating it. Again, a recording of the webinar will be available shortly on the Ocean Ice YouTube channel, and you've heard Soshik project mentioned a couple of times. I'm going to plug a policy briefing happening on the 3rd of May. It will address very similar topics, so I'm doing that because I assume people who are listening here will be interested as well to what they talk about there. So please feel free to follow the Ocean Ice Project. Andrew had some of the social media tags on his slides. It's at OceanIce_EU on Twitter. The EU Polar Cluster, of which Ocean Ice is a member, you can follow them for similar events and announcements at EU Polar Cluster on Twitter. And I just want to say thanks again to everyone, and we'll leave it there.
Thanks all. Thanks very much. And thank you to the EPB for organising.
All right. Thank you. Have a nice afternoon.